Often in integrals we have a term of the form a plus bx squared, and we want to eliminate that term or make it simpler in order to be able to take the integral. Usually this happens if it's by itself. Of course you could use the power rule, but if it was under a square root, or if instead it was over in the bottom of a fraction, then it would not be so simple to be able to take the integral. So in order to handle these cases, we're going to do a certain substitution. We will let a plus bx squared equal a plus a, so you match the constant that's by itself, tangent squared of theta. Now notice that if we do that, then we're going to get, we can factor out an a, 1 plus tangent squared becomes secant squared of theta. And this is going to allow us to take certain integrals that we know would not be able to take otherwise. Notice that what we're actually doing, if we subtract a's from both sides, is we're replacing bx squared with a tangent squared, and we could solve for x to get the square root of a divided by b tangent of theta, taking the square root of both sides. Now actually there should be an absolute value here, but the reason we don't have to worry about that is because what we're really doing is we're letting x equal the square root of a over b tangent of theta, and then working our way back up. Now it's kind of hard to see at a glance exactly the form root a over b tangent of theta. I find it much easier to just do the top line and go down, and we'll just ignore that technicality altogether. So that's going to be our substitution. The other technical detail that I should mention is that we have to say what our theta is allowed to be, because it can't be things that would make tangent undefined. In order to get all possible values of x, we're going to assume that my theta is between negative pi over 2 and positive pi over 2. And the reason why is that the graph of the function, this is my theta and this is my x-axis, and we're arranging theta between negative pi over 2 and positive pi over 2. The graph of tangent, or root a over b tangent, looks something like this, passing through the origin at 0, 0. And that you can see how for those theta values, x attains all real numbers. And so x can equal all real numbers, and the substitution is valid. So again, that's a technical consideration that we won't usually have to worry about. We'll see an example where we will need to think about it a little bit to get rid of an absolute value. But we'll come to that when we get to it. In the meantime, let's start with an example problem where we'll use this particular substitution. We want to find the integral of z squared over 4 plus 9z squared dz. Now, in order to do this particular problem, we note that the 4 plus 9z squared it makes this problem difficult. We could simplify the problem by just letting the bottom equal u, but the problem would then be is I would not have the z dz term that I need on top. I have a z squared on top, and if you try a straightforward substitution, you could see that that would not work out for you. So we're going to instead use this trigonometric substitution trick. We have 4 plus 9z squared, and we want our substitution to turn that into 4 plus 4 tangent squared, which would in turn be 4 secant squared of theta. Alright, we can, from the first term, first equality, subtract 4 from both sides. And then I can divide both sides by 9. And then finally, take the square root of both sides and I ignore the absolute value because what I'm really doing is I'm letting z equal 2/3 tangent of theta, and then going up the chain of equalities, I get the rest of those facts. So I don't need the absolute values since I get to choose that z is the not absolute value. Finally, if I'm going to do a substitution, I cannot forget that I need a dz term. But fortunately, my dz, that would equal 2/3. Tangent has a derivative of secant squared, and then I would get a d theta, because that's my variable on the right-hand side. And that's all I need to do. So now I just take the original integral, and I see I have a z squared on the top, and from this third purple line I see that z squared is equal to 4/9 tangent squared theta all over 4 plus 9z squared. The first line tells me that that's 4 secant squared of theta. Finally, dz is equal to 2/3 secant squared of theta d theta. And I can do some canceling. Secant squared cancels top and bottom. Let's see here, I've got a 4 cancels with a 4, and I don't believe anything else will cancel for me. So let's rewrite. So I've got a 1/9 times a 2/3. So I'll just bring that out here as 2/27. Integral, I guess all I have left is tangent squared of theta d theta. Now I don't know what the integral of tangent squared is, but fortunately I do know my trig identities. I know that tangent squared is the same thing as secant squared minus 1. So I'll make that change. Tangent becomes secant squared minus 1. And that I can integrate. Secant squared is the derivative of tangent. And 1 integrates to theta, because theta is my new variable. Add a plus c because it's a general antiderivative. Now, it's tempting to just put a box around this, call this the final answer, but remember, theta is something that I made up. Up here, we see that we have that I let z equal 2/3 tangent of theta. So, in order to get rid of these tangent of theta and theta terms, I will need to do a little bit more work back up here in my substitution. Back up here, I said that z is equal to 2/3 tangent of theta. Well, let's solve for z. So I can solve for z, I solve for tangent theta. If I solve for tangent theta, I get tangent theta is equal to 3/2 of z. Okay, what else can I do? Well, if I need to know what theta is itself, I can just take the inverse tangent, which I'll denote with a backwards arrow, although many people use a -1 for that same purpose. Inverse tangent of 3/2 z. So now I can make both of those replacements down here. Tangent of theta will get replaced with 3/2 z. Theta will get replaced with the inverse of tangent. So my final answer tangent gets replaced with 3/2 z. Theta gets replaced with the inverse tangent of 3/2 z. And I called that my final answer, but I note that I can distribute that fraction on the left a little bit, and it would cancel a little bit. So we end up with getting 1/9 z minus 2/27 inverse tangent 3 halves z plus c. And there's no way to simplify the 2/27th fraction with the inside of the inverse tangent, so that is my final simplified answer.